We may have misunderstood the universe. Those are not my words. Those are the words of Adam Rees, a Nobel Prize-winning physicist at Johns Hopkins University, a man who has spent his career measuring how fast the cosmos is flying apart. And he's not being dramatic. He's reading his own data and telling us plainly that something in our model of reality does not add up. For nearly a century, cosmology has rested on a single elegant framework. We call it the Standard Model, a set of equations and assumptions that describes everything from the first fraction of a second after the Big Bang. It has worked beautifully for decades, explaining observation after observation with an almost suspicious level of precision. And then the James Webb Space Telescope turned on. What Webb found did not confirm our understanding. It complicated it. In some cases, it contradicted it. And the deeper we've looked with this telescope, the wider the cracks have become. The trouble starts with a number. It's called the Hubble constant, and it measures the rate at which the universe is expanding right now. Not in the past, not in some theoretical future, but right now, today, at this moment. You'd think a single number like that would be easy to pin down. 2 methods, 2 teams, same universe, same answer. That's how science is supposed to work. It didn't. And this isn't the first time. The Hubble constant has been causing arguments since the 1920s, when Edwin Hubble himself first calculated it. His original estimate was so far off that it made the universe appear younger than the Earth. For decades after that, 2 camps of astronomers fought bitterly over whether the true value was closer to 50 or 100. A disagreement so fierce, it split the field in half. By the early 2000s, the number had finally converged. Everyone agreed it was somewhere around 70, give or take. The war was over. The measurement problem was solved. Except, it wasn't. Because as instruments got more precise, a new split emerged, smaller than the old one, but far more stubborn. The first method looks backward, way backward. The European Space Agency's Planck satellite spent about 4.5 years mapping the cosmic microwave background, the faint afterglow of radiation left over from when the universe was about 380,000 years old. From that map, physicists extracted the conditions of the early universe, plugged them into the Standard Model, and ran the equations forward nearly 14 billion years to predict how fast the universe should be expanding today. The answer they got was about 67 kilometers per second per megaparsec. A megaparsec, by the way, is 3.26 million light years. So for every 3.26 million light years you look outward, galaxies are moving away from us 67 kilometers per second faster. Clean number, tiny margin of error, confidence level through the roof. The second method is more direct. Instead of modeling the past and projecting forward, it measures the present. Adam Rees and his team, called SH0ES, use a technique known as the cosmic distance ladder. They start by measuring the distance to nearby pulsating stars called Cepheid variables, stars whose brightness fluctuates at a rate directly tied to how luminous they actually are. Measure the pulse, calculate the true brightness, compare it to how bright the star looks from Earth, and you've got a distance. From there, they step outward to galaxies containing both Cepheids and a specific type of exploding star called a Type 1a supernova. These supernovae are useful because they all explode with roughly the same peak brightness. So once you've calibrated them with Cepheids in the same galaxy, you can spot them in galaxies hundreds of millions of light years away and calculate how far those galaxies are. Combine that with how fast they are receding, and you get the Hubble constant. Rees's team got 73, not 67, 73. 6 kilometers per second per megaparsec faster than the standard model predicts. That might sound like a rounding error. It is not. In a field where measurements are routinely precise to within 1%, a gap of 8 or 9% between two independent methods is enormous. It's the difference between a universe that's about 13.8 billion years old and one that could be more than a billion years younger. It changes the size of the observable universe. It changes the rate at which galaxies are separating. It changes, potentially, the nature of the dark energy that's been pushing everything apart since the late 1990s. Think about what that means for a second. If the universe is expanding faster than our best model predicts, then everything downstream of that prediction shifts. The age of the universe gets younger. The distances between galaxy clusters change. The timeline for when the first stars ignited. When the first heavy elements were forged inside dying suns. When the conditions for planets, chemistry, and eventually life became possible, all of it shifts. You're not just adjusting a dial on a dashboard. You're redrawing the entire history of everything that has ever existed. For a while, scientists assumed someone had made a mistake. The most popular theory was stellar crowding. Cepheid variables tend to live in the dense, dusty disks of younger galaxies. When the Hubble Space Telescope looked at them, its cameras sometimes blended the light of nearby stars together, making the Cepheids appear brighter than they truly were. Brighter Cepheids mean shorter calculated distances. Shorter distances mean a higher Hubble constant. If you could clean up that blending, the argument went, the tension would relax. So Rees pointed the James Webb Space Telescope at the same stars. Webb orbits the Sun about 1.5 million kilometers from Earth, far beyond the interference of our planet's atmosphere and thermal radiation. Its 6.5-meter gold-plated mirror collects infrared light with a sensitivity that makes Hubble look like a pair of reading glasses. If any telescope could settle this, it was Webb. The expectation among many in the field was that Webb would gently deflate the tension, that its sharper vision would reveal the blending, correct the distances, and bring the Hubble constant back into line with the standard model. Some astronomers were already drafting the obituary for the crisis before the data even came in. Webb's infrared cameras can cut through dust and crowding with a precision Hubble never had. If blending was the problem, Webb would show it. The Cepheids would look dimmer through Webb's eyes, the distances would stretch, and the Hubble constant would drop back towards 67. Crisis averted. That is not what happened. Webb confirmed Hubble's numbers, not approximately, but almost exactly. The Cepheids look the same. The distances held. The expansion rate stayed at 73. In early 2024, the SH0ES team published a paper in the astrophysical journal Letters, announcing that they had now spanned the full range of Hubble's Cepheid observations with Webb, extending all the way out to a galaxy called NGC 5468, about 130 million light-years from Earth. 1,000 Cepheids across 5 host galaxies of 8 supernovae. The conclusion was unequivocal. Measurement error could be ruled out with very high confidence. Rees put it simply. With the errors eliminated, what's left is the possibility that we have misunderstood the universe. At a 2019 conference at the Kavli Institute for Theoretical Physics in California, Rees asked David Gross, a Nobel Laureate in particle physics, whether the field should start calling this discrepancy a problem. Gross corrected him. He said they shouldn't call it attention. They shouldn't call it a problem. They should call it a crisis. By December 2024, the crisis had deepened. Rees's team published their largest Webb study yet, using data collected across the telescope's first 2 years of operation. They employed 3 separate methods to measure distances to supernova host galaxies, cross-checking Cepheids against carbon stars, and a technique called the tip of the red giant branch. All 3 methods agreed with Hubble's original measurements. All 3 pointed to a universe expanding faster than the standard model allows. So either the model is wrong, or something is hiding inside the physics that we haven't accounted for. Not everyone agrees the tension is even real. Wendy Friedman, an astronomer at the University of Chicago, has spent years building an independent distance ladder that relies less heavily on Cepheids. Her team uses additional types of stars, red giants, and a class called JAGB stars that are found in less crowded regions of galaxies and are less likely to be affected by dust and blending. When she submitted her own Webb analysis in August 2024, her 3 methods gave different answers. The red giant and JAGB methods landed around 68 to 70, consistent with the standard model. Her Cepheid measurement came in higher, near 72, but with larger uncertainties. Her overall combined result was about 70, sitting in a kind of no man's land between the 2 camps. We're living inside a question. The most precisely measured universe in history is telling us 2 different things at the same time, and both of them appear to be correct. Something in those 14 billion years we've never directly observed is doing something we don't understand. Some ingredient we haven't identified, some process we haven't modeled, some property of space-time we haven't imagined. Cosmology has been here before. In the 1990s, the field nearly collapsed under the weight of a different contradiction. Measurements suggesting the universe was younger than its oldest stars. That made no sense. The stars couldn't be older than the thing they lived inside. Then came the discovery that the expansion of the universe was accelerating, driven by dark energy, and the whole picture snapped into focus. What looked like a fatal flaw turned out to be the shadow of something enormous that nobody had seen yet. That's the thing about crises in physics. They feel like endings, but they almost always turn out to be doors. If you could somehow stand outside the universe and watch this moment, you'd see a species on a small rocky planet, orbiting an unremarkable star in the outskirts of a mid-sized galaxy, using mirrors and mathematics to argue about whether reality is expanding 6% faster than it should be, and caring deeply about the answer. That's either absurd or magnificent, and honestly, it might be both. This isn't failure, it's the opposite. This is what it looks like when a science reaches the edge of what it knows and keeps going. The universe isn't broken. Our map of it is just incomplete. And whatever comes next will almost certainly be stranger and more beautiful than anything we've imagined so far. Thanks for watching, and I'll see you in the next one.